Finding a specified term of a geometric sequence given the common ratio and first term. Before we get started here, I do want to remind you that you've studied the things of exponential decay. For instance, if I give you a short graph here, here's f of x, there's the f of x axis, and here's the x axis. And you may have studied the function f of x equals 1/2 raised to the x power. And that's obviously an exponential decay. It'll go something like this, approaches the x-axis. Well, in some ways, sequences just represents certain ordered pairs. If you just look at n equals 1 and n equals 2 and n equals 3, then we're going to see a sequence of dots here that are actually approaching 0, right? The y value would be 0. It's approaching the y value to be 0. If you go to 4, the values are getting lower and lower and lower. And of course, if you calculate that, it will indicate that as well. If you take f of 4, you get 1/2 raised to the 4th power, which is 1/16. So certain patterns, these little blue dots, sometimes they run in a very, very nice pattern, and they're worth investigating. Sequences is actually the introduction of something called series, and you're going to see series pretty soon as well. So let me try to give you an example of those blue dots, but instead of seeing it as a decreasing exponential decay function, why don't we draw some geometry? After all, we are looking at geometric sequences. So let me erase the board here. And I'm going to show you the pattern of those blue dots in a very, very different way now. I'm going to first start off with a 1x1 square. And it's 1 unit by 1 unit. 1 by 1. And if it doesn't look square, pretend it is a square. Looks like I drew it too long. I draw it right here. And let me erase these extra blue dots. So there is a 1 by 1 square. Now what I'm going to do is cut that in half. And now you're going to see the base of 1/2. But what happens when you cut 1/2 again? Let's cut 1/2 again. This time we go this way. And now you get 1/4. And what happens if you cut 1/4 in half? Well, then you get 1/8. And what if you multiply 1/8 by 1/2? Then you get 1/16. What if you take that 1/16 and multiply it by 1/2 again, or cut it in half? You get 1/32. And what happens if you cut 1/32 in half again? Then you get 1/64. So are you seeing a pattern here? Obviously, this is counting numbers according to the base of 1/2. It's also a ratio too. You could see the ratio of 1/2 as well. Now here's the question. I'm going to ask you this. So here's a sequence of numbers. 1/2, 1/4, 1/8, 1/16, 1/32. Now I'm just simply going to put a plus sign in between here. So they were a sequence of numbers and with a very, very specific pattern. Now obviously if we stop at 5 terms, you could easily find its sum. Now I'm going to ask you to not stop at 5 terms. I want you to put 3 dots at the end and never stop adding these terms. What would happen? Keep adding those terms. The next one would be 1/64. The next one would be 1/128. Keep doing that and see what happens. In other words, ask yourself this. Does the sum exist? And I'm going to tell you something. The answer is on this page. I'll let you think about it. I'm going to go back to geometric sequences. Let me clean up the board here. Let's look at example A. Find the ninth term of the geometric sequence whose common ratio is 1/2 and whose first term is 8. The first thing you want to do is actually write the definition of a geometric sequence. A sub n is equal to a sub 1 times the common ratio raised to the n minus 1 power for n equals 1, 2, 3, dot, dot, dot. Now remember that is the domain of this function. Okay, it would just graph the outputs of dots, or the output that consists of ordered pairs, right? It's a discontinuous function. Okay, well, we already know the first term. We know that the first term, a1, is 8. We also know that r is equal to 1/2. And we want to find the ninth term. So first of all, I'm going to write the formula, or the sequence. Here's the function. A sub n is equal to 8 times 1/2 raised to the n minus 1. That's not my final answer, but this is necessary work. Now we're going to find a sub 9. We want the expression a sub 9. A sub 9 would then be what? 8 times 1/2 to the 9 minus 1, which is 8. And of course, you could take your calculator there and get this final expression. An exact answer would be 8 over 2 to the 8th power. 2 to the 8th power is pretty big. 8 over 256, which reduces to 1 over 32. I'm going to put a period here. Therefore, a to the ninth is equal to 1 over 32. I'm going to circle this as well. You really should write that. Write your function, or write the geometric sequence. Find a 10th term. Oh, I should circle all the work in between. Might as well just circle everything. Let's do example B. If you want to, you could pause the video and try it yourself, and then unpause it to check your answer. Find the 10th term of the geometric sequence whose common ratio is 3/2 and whose first term is 4. Once again, we can write the definition. B sub n is equal to b sub 1. How about that? B sub 1, common ratio, times the common ratio raised to the n minus 1 power. And we know r is equal to 3/2, and the first term is 4. B sub 1 is 4. So let's write our sequence, our geometric sequence. 4, base is 3/2, or the common ratio is 3/2, and then raise it to the n minus 1 power. I'm going to circle this, even though it's not the final answer. We want to find b sub 10. B sub 10 is an expression. We're just going to manipulate this expression here and raise to the 9th power. Let's see what this gets. This is 4, which is 2 squared. So we have 3 to the 9th over 2 to the 7th. And let's see what that is. And since there are no common factors, there are no common factors. 2 and 3 are prime numbers, so that will be the final answer. Therefore, b sub 10, your final expression is b sub 10, which is 19683 over 128. Circle our answer in our work, and we're done.